So our group made a keyboard synthesizer on the FPGA, and I'm going to be demonstrating the features of it. So the volume's low right now, but if I turn the volume up, you'll be able to hear. And right now we're playing a C, and as you see on the 7-segment display, we're displaying the note name here, the octave number, which is 4, and then the type of wave. Right now it's a square wave, so it makes that animation. And then I can change the note using these keys here. So if I want to play a different note, I press this, it just went to a D, as you can see here, and on the 7th segment. Everything's changed. We're still at the same octave though, so that's not going to change. And then I can just play all of the standard 12 notes of the keyboard, so E.
And then here, he starts rapidly pushing it, so it's not going to register those. So basically,
and then the sharps. And if I want to go up an octave, or if I want to change the octave, we're using these number row keys. So right now we're at octave 4, so we're going to go up an octave, I click 5, and we just went up an octave, the note's the same.
You delete it,
Or 6, or 7, or we can go lower, like 3 and 4, 2. We can also just increase the octave by 1, and we can play scales using that. So we use the L and the A keys to do that. So if I start at like C, we can go play a full scale. So we just play a scale there, and we can also go down with the scale. So if we start at B, starting at B, we can go down the scale.
Does the testbench have inputs?
We can also change the waveform type. So right now we're playing a square wave. We want to change it to a sine wave. We click there, and as you can hear, kind of it sounds different than the square wave. And here our animation also changes, so it looks like a sine. And we can just play using the sine wave instead. Everything else is pretty much the same, except the waveform is just different now. Lastly, we can change the display mode. So now the display mode shows the frequency. It just shows the note, which is F, and then it shows the frequency. So if I play like a...
So you have button input, but it's not encoded.
Or sorry, that's not the note. That's not the number. This is just the frequency. But if you see, if we like look at this frequency and this value, they're pretty similar. Just let it calibrate. Yeah, so it's showing accurately that we're playing the right frequency. And the reason we laid it out like this, it was because it's pretty similar to how a real piano is set up, with all of the white keys below the black keys. And we wanted to just have everything pretty intuitive and make it easy to play.
Double 0, 100, 10. How will you declare it? Initial begin. Every time you just change it. Just to be simplified. I'm not sure.
Okay, so I'll briefly run through our top module and some of the inputs we take, as well as some of the values we store. So first, there are these two inputs for the PS2 keyboard, which are PS2 clock and PS2 data. Of course, we use a 100 megahertz clock from the FPGA, and then we have the outputs for the 7-segment display. So we store two values throughout this module, which are the note and the octave. So the note is stored in a 4-bit register because we have 12 notes, and then there's the octave, which is stored in a 7-bit register. So moving down, here is where we bind keys to the keyboard. First, there's this PS2 receiver module that we got from online, and we changed a bit to have this key flag because we were having some issues with it. So that just takes a 50 megahertz clock, and that takes a PS2 like serial signal basically from the keyboard, and it converts it to a 32-bit key code that's unique for each key press. And so that's what we look at down here to bind different functions to each key. So here are some letter keys, S, D, F, G, H, and these represent the white notes on the piano just up here. As you can see, we only look at 8 bits of the key code because that's all you need. And so yeah, the notes get bound to those. So the notes are in terms of the tones, and there's 12 tones, but basically since it's laid out like a piano, it's not 1 to 1 here, so it goes 0, 2, 4, 5, because these are all the white notes, and then the black notes are in between, and so those are down here. Those go 1, 3, 6, 8, and then we have our smart octave buttons here, which are on the A and L keys. So if you hit the L key, the octave will increase by 1 and the note will go to 0, and that's what will let you play that whole octave. Right here we have some buttons for the octave that are just like the number keys, so you hit the number key and then the octave goes to that one. Rounding out the keybinds, we have the number keys bound to different octaves. So really it's octave 1, 2, 3, 4, 5, 6, 7, but we have them stored by tens because we had some bugs when we stored them as like 1, 2, 3, 4, 5. So these are here so that you can easily press like the key 4 if you want to go to the next octave or you want to jump around and stuff. And then lastly here we have Z and X bound to modes 0 and 1, and those are to display either the note and the octave on the 7-segment display with the pattern of the wave, like the square wave or the sine wave which we showed, or you can go to mode 1, which shows the frequency of the note. And then B, N, and M are set to the 3 different wave forms we have. So the first waveform is a 50% duty cycle square wave. The second waveform is the sine wave, and then the third waveform is the triangle wave, which we didn't get working quite well. So I'm Alex, and I worked on all these keybinds.
In top module, we have this smart scales feature where if you play the last note in a scale, then it will increase the octave for you and play the note that it's supposed to. And it's bound to A for increasing the octave or L for decreasing the octave. We set this octave flag to 1 if we're increasing and 0 if we're decreasing. Then in note generator, we're checking if it's 1, then every interval between the octaves, which would be 5, 15, 25, is set to the higher octave. So here this is set to the value of 10, not 0. And here, if it's 0, that means we're decreasing octave. It's set to the lower one. So 5 is between 10 and 0, but it's set to the 0 value. Also in top module, we tried adding these features where if you play the numpad keys, it would go up by a certain interval. So this would be a minor third, or a major third, or a major fifth. Unfortunately, we couldn't get this to work because it would sort of break the keyboard because it kept remaining in this mode where it kept trying to increase the interval every time. So this wasn't included in the final demo, but this could have been a useful feature to have because it would easily allow you to play these common musical intervals. I'm Ethan, and I worked on the smart scales feature, and I tried to fix this part.
Okay, this is the note generator module. So here we have a lookup table that we use for, firstly, just for the bass notes in the 4th octave. We do simple math, right, for increasing by octave, so we don't have to have a ridiculous 7 times 11 lookup table. We only have just the one lookup table here. We talked about in our presentation a little bit that a 50% duty cycle is very easy to set to create because you're just dividing the clock. So this is a very important line in the code because it's the reason you're able to hear anything in analog. Now we also wanted to include a different kind of duty cycle just to be able to compare. So this is the sine duty cycle. This one's a lot more complicated to do because we use another lookup table here. which is just a percentage of a sine wave. So this adds up, it multiplies for every clock cycle. It changes the width of the pulse, which creates a different sounding note. We tried to implement a triangle sine wave, but we're not able to do it. We think it should be working, but we're not experts at analog audio, so it was difficult to even get this one to work because it's very specific based on the frequency of the clock, which is why we have all these different factors here while we're testing to try to get some kind of wave. But now we're able to hear different notes, hear different octaves, all using the sine wave as well as with the 50% duty cycle, which is just a basic square wave.
So this is the display mode module, which is used to define the types of things that are going to be displayed on the 7-segment display. So first off, we have the definitions of what's going to be displayed. So it's the note, the octave, and the frequency. And next we have the definitions of each of the individual digits of the 7-segment display. So that comes from left to right. And then we have definitions for the actual output types, whether it be underscores or dashes, which are going to be used to create the waveforms for the animation that define what kind of waveform is being used. Now we have the breaking up of the frequency into individual digits. That is going to be stored into each of these individual regs to be able to display it properly on the 7-segment display. And here is the first mode. The first mode that we define is to show the output type, which is the note being played, as well as an animation on the right-hand side of the display to define the output type. The case statement operates by taking in the input of the note type and outputting the defined, whether it be C, etc., of which type of note is being played. And then down here we have the animation, which is being displayed on the right-hand side of the 7-segment display. So whether it be a square wave, sine wave, or triangle wave. So the square wave operates by taking in what type of wave is being played and then displays in 2 steps the square wave. So that would be, for example, we have the underscore and then the line at the top on different steps, and then it oscillates through that in order to create the animation. And then here we have the second case statement, which is used to display the frequency of what's being played. This takes in the input and divides the frequency into each individual digits, and then uses modulus to make sure that we're actually displaying a single digit. And this would be the same for would be different for each of the individual octaves. So as the octaves increase and decrease, the actual frequency increases and decreases corresponding by multiplying by 2 or dividing by 2. And then we have the default state, which is where nothing is being displayed because nothing has been played thus far.